Hi, my name is Ankit Singh, and I'm a sophomore chemistry major. A fun fact about me is that I'm part of the Residence Hall Association here at Carolina. I want to be a chemistry LA because I plan on pursuing a PhD after I'm done undergrad. I think the teaching experience of being a chemistry LA will really help me in my further career during my PhD and even further on. One way that I would help students better study for chemistry is by encouraging active learning. I would try to help them understand the content during lectures so that they don't have to spend too much time outside of class re-reviewing content, and they can instead use that time to efficiently practice and solidify these concepts for themselves. So, I'll be solving this acids and bases problem. Let's get started. So in this problem, you're titrating 0.25 molar, a 10 ml sample of a 0.25 molar weak acid solution with 0.5 molar of a strong base NaOH. So for part A, it asks you which of the diagrams most closely represents the solution before any of the strong base is added. So to answer this, you have to consider what's in the solution before you add any of the strong base, and that is your weak acid and water. So when you have a weak acid in an aqueous solution, you expect to see a lot of the weak acid and very little dissociated protons and anions. And the diagram that best represents this is X. Now, to find the pH of the solution before any of the strong base is added, you would use an ice table based on this Ka formula right here. So I already have the ice table set up, and from there we find that your Ka is equal to x squared, because at the end of your disassociation you get an x amount of A minus and an x amount of H plus, which then you multiply them together and you get x squared with your initial concentration of your weak acid minus x, because that's how much of it disassociates. Now this x value is very small, so when you're solving this problem, you can consider it on the bottom to be 0. So you get x squared over 0.25 is equal to your Ka, which is 4.0 times 10 to the negative 6th. And by solving for x, you get your x, which is equal to your H3O plus concentration, which you find it to be 1 times 1.0 times 10 to the negative 3 molar. Then you take the negative log of that, and you find your pH to be equal to 3. Now, the next question asks which of the above diagrams represents the solution at midpoint, which is 1/2 equivalence. And so this means that at the midpoint you have added enough strong base to where your strong base concentration in the solution is equal to 1/2 of that of your weak acid. And when you add 1/2 concentration of the strong base, this means that 1/2 of your weak acid is going to disassociate into protons, because it'll be giving its protons away to the strong base, which has a strong affinity for those protons. And this is best represented by diagram Z. Now we're asked to find the solution, or the pH of the solution at the midpoint. In order to do this, we're going to use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation tells us that the pH is equal to the pKa plus the log base 10 of the concentration of your anion over the concentration of your starting acid. And because we're at 1/2 equivalence, the concentration of your anion and the concentration of your starting acid are equivalent, which means that your log base 10 turns into the log base 10 of 1, which is 0. And what you end up finding from that is that your pH at your midpoint is equal to your pKa. And you get your pKa by taking the negative log of your Ka, which in this case gives you a pH of 5.40.